In this video, I'm going to explain you one more example of a vector space. So here I'm taking let V be a vector space over the field F, okay? And S be a set, let W equal to vector space be the set of all mappings from S to V. Means I'm taking S to be a set and I collect W to be nothing but function from S to V. Means I'll collect all types of function from S to V under and define addition and scalar multiplication in W pointwise. We are defining this addition and scalar multiplication in pointwise. That is, f is a function from S to V and g is also a function of S to V. Now we'll define what is f plus g. Okay, we are trying to define what is f plus g. So f plus g is also a function from S to V. Okay, f plus g is also a function from S to V given by f plus g apply on S, an element from here. This will be f of S plus g of S. In the same way, the scalar multiplication alpha f is also a function from S to V, and where alpha is from the field is defined by alpha of f applied on S is nothing but alpha fs. So using these two definitions, we try to show it is a vector space over the field F. So we are going to prove that it is a vector space over the field F. Okay. So in over the field F. So we take let W be a non-empty set. So I'm taking W to be a non-empty set. First of all, it should be a non-empty set. Now I take three functions. Okay, so f, g, and h belong to W, and I take one element from S. I will first of all I will show that W plus is a vector space. Okay, W plus is a vector space. So f plus g apply on S by using the first definition. We have fs plus gs. Okay, then addition of two function is always commutative, so we get gs plus fs. That is g I can take s I can take out, so we get g plus f applied on S. So this is about the abelian. Okay, so under addition the function is always abelian. Addition of function is abelian. So the next one is about the associative. Okay, so f plus g plus h applied on S. So this is nothing but f plus g applied on S plus hs. Okay, h applied on S. So again you apply here, so by using the first definition, this will be f applied on S plus g applied on S plus hs. Okay, so addition of function is always associative. Okay, so we can interchange the brackets. So we have interchanged the bracket here. So we get here fs g plus h applied on S. So that is nothing but f plus g plus h applied on S. So we got here that it is associative as well as it is commutative. Okay, so here it is commutative and associative. Addition is commutative as well as associative in W. Okay, so we'll try to find the additive identity. So I take a function from S to V such that I define every element of the function z is sent to 0. Okay, then we have here f plus z applied on S, then f of S plus z of S. Z of S is what? It is 0. 0. Here, so we are taking here 0. So fs plus 0, we get fs. That shows that f plus z is equal to f, which is equal to z plus f. So z is nothing but it is an identity element, and that is the zero mapping. Okay, that is your zero mapping. Therefore z is the zero element of addition in W. Okay, and let us find the inverse of this function. Suppose I take f dash is the inverse of f. Okay, so f dash I am defining from S to V, defined by f dash s is defined to be minus of fs for each s belongs to W. Now I'm taking f plus f dash s, so this will be fs plus f dash s. Okay, f dash s. Now f dash s, I have defined f dash s to be equal to minus fs. So in place of f dash s, you write minus fs. So fs minus fs will get 0. So that shows that f dash is the inverse of f. So here we have f dash is the inverse of f. So every element of W has an inverse, and it is commutative under addition as well as associative. So hence it is a abelian group. Okay, W plus is an abelian group. Now we'll try to prove the condition of the vector space, the 4 conditions. So I'm taking 2 functions from W and 2 scalars from F. Okay, so first alpha F plus G apply on S. Okay, so this is nothing but alpha will come out, F plus G applied on S by the second definition. So Fs plus Gs. So you can separate this alpha, you can multiply to this. So alpha Fs plus alpha Gs. So this is nothing but by definition of, but if you reverse the second definition, what we have, we'll get this nothing but alpha F applied on S, and this is also, if you reverse, we get alpha G applied on S. So that you can take S common, so we get alpha F plus alpha G applied on S. And the second, these two are equal, so the first condition is true. Let us check the second condition. Alpha plus beta F applied on S by using the second definition. Okay, by using the second definition, alpha plus beta will come out and we have Fs. Fs you multiply to this, so we get alpha Fs plus beta Fs. So if you reverse the second definition, this is nothing but alpha F applied on S, and this is also beta F applied on S. So S you can take out, so we get alpha F plus beta S applied on S. And if we so the second condition is also true. Let us check the third condition. So we have alpha beta applied on F S. So using the second definition, alpha beta will come out and F applied on S. So alpha, these are elements, so we can interchange the brackets. So we get alpha beta applied on Fs. So by using the second definition in the reverse order, we get beta F applied on S. Again, if we use the second definition in the reverse order, we get alpha beta F applied on S. So we got that alpha beta F is equal to alpha apply bracket beta F close bracket. So the second condition is also true. Let us check the third condition. 1 into F applied on S, that is nothing but 1 into Fs. So 1 into Fs is nothing but Fs. Okay, so we have proved the fourth condition also. Means we have proved all this condition. Alpha F plus G is equal to alpha F plus alpha G. Alpha plus beta F is equal to alpha F plus beta F, and alpha beta F is equal to alpha beta F. 1 into F is also equal to F. So all the 4 conditions of a vector space is satisfied. Hence W is a vector space over the field F. Thank you.